Okay, so here we're going to check if the mean value theorem can be applied to a function f on this closed interval AB. And if so, find the value c in AB that is guaranteed by the mean value theorem. So let's recall what the mean value theorem is for just a second. All right, so the mean value theorem says this. If f is continuous on the closed interval AB, okay, so it's continuous on the closed interval, and it's differentiable on the open interval AB, then there exists at least one c such that f prime of c is equal to f of b minus f of a all over b minus a, right? Okay, so that's what the mean value theorem says. So can we even apply the mean value theorem? We check this first. If I can't do that thing first, then by golly, I can't do this, okay? So it's an if-then statement, right? So if this is true, then this is true. Okay, if I can spell then, right? Okay, so you think of it this way, all right? If I have keys to a Ferrari, then I can put those keys in the ignition, start it, and drive off, right? But if I don't have the keys, then I can't even get into that beautiful machine, right? So unless you've got the keys to the Ferrari, you can't drive off with this formula here. Ha ha ha. Okay? So that's how I think about it with an if-then statement. It's conditioned on the hypothesis. So I have to first verify that f is continuous on AB, closed interval, and then differentiable on AB. Okay? So to do that, I look at my function. What is my function? F of x is 1 over, oh, it's irrational. Now, this denominator here factors, and as you can see, it factors to x minus 2, x plus 1. Once again, if you're having trouble factoring, I always tell you to go to the video in college algebra, but I guess I can do one of these, right? Trinomial, I want it to multiply to negative 2 and add to negative 1. Well, if I do negative, that's not writing. Okay, if I do negative 2 times 1, that gets me negative 2, and negative 2 plus 1 gets me negative 1. So my factors there are x minus 2, which that's where the negative 2 comes from, and x plus 1, that's where that positive 1 plus 1 comes from there. Okay, so that's how I did it. All right. There's a longer way to do it through the AC method that's not guess and check, and you can watch the AC method on my college algebra page if you're interested in that. So what does this mean? So what do I know about rational functions? Well, with a rational, I know that the rational function is only defined where the denominator does not equal to 0. So as long as this isn't equal to 0, we're okay. Does this equal 0 anywhere? Well, absolutely it does. If x equals 2, that's bad. That's going to give us dividing by 0. But also, if x equals, let's see, x plus 1 equal to 0, x equals negative 1 is also bad too. So negative 1 and 2 are numbers that are not in the domain, okay? If I plug those in, it blows up, so it's not continuous. F is not continuous at those values. So F is continuous for values, if you think about it as a number line, negative 1 was bad and 2 was bad, right? So I got to jump over negative 1 and I got to jump over 2. But everything up to negative 1 is okay. Everything between negative 1 and 2 is okay. And then everything from 2 to infinity is okay. And if you remember from college algebra, in interval notation, we use the U for union to combine everything together here, okay? And so that's where this F is continuous on this interval here, all right? So it's split up into 3 pieces just like I drew in that little picture there. Okay, now, why can we not apply the mean value theorem? Well, the mean value theorem can't be applied because it's applied on 1 to 3. Well, what do I know? At 2, I have a discontinuity. If I plug in 2, I'm dividing by 0 here, buddy. And the mean value theorem says that it's got to be continuous on that interval a to b. Well, it's not continuous at 2. Therefore, I cannot use the mean value theorem to find a C value. So you got to be careful. In order to drive the Ferrari, you got to make sure that you got the keys first. And if you don't have the keys, if it's not continuous or it's not differentiable, then you can't drive the Ferrari. You can't use the mean value theorem. So let's try another problem. Let's do one now where we actually can do it. That way, I wanted to show you an example where it didn't work and then one where it does work. Okay? So this is on the closed interval 1 to 7. And so what do we know about the natural log of x? Well, the natural log of x, the graph kind of looks like this. It's defined for 0 to infinity, right? So this thing is continuous on 0 to infinity. So if it's continuous on 0 to infinity, is it continuous from 1 to 7? I think so, right? So it's continuous on 1 to 7. And it's also differentiable on 0 to infinity. How do I know that? Whoa, hold up. Didn't mean to do that. How do I know it's differentiable? Well, golly, what's the derivative of ln x? The derivative of ln x is 1 over x, right? 1 over x is like this here. The only place it's equal to 0 in the denominator is at 0. So from open interval 0 to infinity, looks like we're pretty smooth and continuous here, right? So we're good to go. So is it good on 1 to 7? Absolutely it is. Okay? So therefore, this satisfies the mean value theorem. We've got the keys to the Ferrari. We can plug in our thing. Well, what do we know? The derivative of g, the derivative of ln x is 1 over x, like I just found. So what does the mean value theorem say? It says g prime of c, where c is some number between 1 and 7, right, is equal to g of b minus g of a, where this is g of 7, because that's a and b, right, minus g of 1 over 7 minus 1, okay? Now I'm going to apply this in here, and so what is that? The derivative evaluated at x is 1 over x. So the derivative evaluated at c is 1 over c. Okay, you see the analogy there? And then this is equal to, what is g of b? Well, the function g is ln x, right? So g of b would be ln b, which is ln 7. Okay, remember a and b here. Divided by g of a, which is ln 1. I'm sorry, minus ln 1. And then divided by b minus a. Well, b is 7 minus 1. Okay? And when I do this math here, I have ln 7 minus ln 1. If you type ln 1 into your calculator, that's 0. So it's just ln 7 in the numerator. And then 7 minus 1, if you got to type that into your calculator, well, you get 6. Okay? And so this right here, remember what this represents. This number represents the average rate of change over the interval from 1 to 7. And so remember, when I'm talking about the mean value theorem, and I'm talking about average change from, from 1 to 7, right, or whatever it is, I'm looking for what is that C value that has the same slope as my average change slope does, okay? So I'm looking for some C in there that has that same average slope, okay? So how do I do this? Well, I need to solve for C. So I have 1 over C equals ln 7 over 6. If you want to, you can butterfly this bad boy. I mean, this is silly to call it butterfly, but this is how a lot of people learned it. That means they cross multiply, whatever you called it back in 3rd grade. This gets you what? It gets you C times the natural log of 7 equals 6. Now, how do I get C by itself? I divide both sides by ln 7. So my answer is 6 over ln 7. Okay? And that's all there is to it, folks. All right.